Thanks for being here after lunch. This is a Preloading Insecurity in your Electron. My name is Luca. So today we're going to cover just a bit of Electron overview. Particularly, we'll be spending a few minutes on the security model, which is particularly important in order to understand the new techniques that I'm going to introduce. We'll dive then deeper into the core topic, which is subverting application via insecure preload. After today's presentation, if you find an XSS, a cross-scripting on an Electron application, you should be able to turn it to RC, even though the application is using the latest version of the framework and all the recommended security settings. So what I will be introducing today are a set of techniques that can be leveraged even in what you consider a securely configured Electron application. So let's just jump into the topics. Before that, this is the experience that was born as a bit of as part of the research time that I spent at my company, Insecurity, as well as customer engagement. So you will see a lot of vulnerability here on common applications. But before, as I said, I just need to do an introduction about Electron. I assume you know what is Electron since you are here. If you don't, it's a popular framework that allows to build desktop app with web technologies. It is really the combination of using Chromium. It used to be libchromium content, so you share the library. Today it's a Chromium binary with Node. And both those components share the V8, which is the JavaScript engine. And even if you don't know the framework, you probably have at least one application that is running on top of Electron on your computer today, whether you're chatting through Skype, Discord, or writing code or text on Visual Studio Code or Atom, and many other applications. It's becoming very popular, and a lot of the applications that don't seem to be Electron-based application, they are actually on top of this framework. So it makes sense from a security standpoint, look at the security of those applications because they're becoming predominant in the desktop environment. And of course, it basically tried to cover the mantra that we've been trying to have for the past decades around with Java of write once, run everywhere or run anywhere. We would really like to have something that we can use to have applications that can be ported between operating system, and they just don't require anything else than compiling and bundling for a specific operating system. And with Electron, it is possible, and moreover, it is possible to do web technology that of course are very popular today, and a lot of people know how to code with those. So here you have an example of why people love it. Felix is one of the core maintainers. He even made an Electron app that is actually running Windows 95, and being an Electron app can be ported on all operating systems. On the other side, you have security people where they're comparing, for example, Electron with the new Flash. And so it's very difficult to taking a stand, but I will start saying it's difficult to fill the gap between web and desktop, and we'll see why. So if you take an Electron application, what you're actually looking at, it's a bundle of a lot of things. It starts from the foundation, Chromium and Node.js, the framework itself, obviously your code and all the NPM, so all the dependency you're bringing in. And every time you move an application, you are moving all these components. So this is an important thing to remember. Applications are bundled through files called .sr that are basically archives, non-compressed. It's a concatenation of files to basically have a single file that will contain the entire application. And the way Electron works is by inspecting those packages, looking for a package of the JSON manifest file, which will determine the main process. So the first process that's executed by the framework. And when you build the main process, as a developer, you're supposed to create a render process. So processes that will actually contain the actual web content. And as of today's, with today's releases of Electron, there are 3 ways of creating render process. The most common one being the browser window. Browser view, it's a recently introduced object that is equivalent to what it was web view tag. Web view tag is a custom HTML tag that is understood when you run some content inside an Electron context. And what is important is that inside the render process, the application will load the resources, right? So we'll load HTML, JavaScript, and CSS. And before loading that content, it can invoke what's called the preload. And this is the central topic of today's. So let's dive a bit deeper into what is the preload. So preload is basically a way to execute code just before the render, finish the bootstrap and start rendering the content. So, you have the main process running, will instantiate, for example, a browser window, as you can see on the code example here, which is, by the way, taken from the official documentation. And the browser window will be instantiated with some preferences, and one of them, one of those preferences is the preload, where we define a file that is executed just before loading resources. And then this is pretty common, particularly around augmenting the DOM, and particularly the window object with custom function. They are normally not available on the browser window. So in this case, for example, you see how you could create a customized window open. So you basically override the functionality of window.open. And an important aspect here is that the preload script, by its nature, has access to Node.js API. Let me now introduce another flag, which is important for other discussion later on, and that's context isolation. Context isolation is a feature that is considered experimental, but it's there and will be there. They basically introduce context isolation between the preload script and the render. What that means is that the preload script can still access the entire window object, but cannot make changes. So if you try to append, like in a previous example, a new version of the window open function, that won't simply work. And moreover, context isolation works on both renders and preload, but also on renders and the Electron framework code. And this is, again, an important aspect, and we'll see why. So let's look at an example of how this works. So you probably see here. So this is some demo code. This is a very useful tool, Electron Fiddle, that allow you to basically run the same code on different Electron versions. So on this side here, you see the main process. This is what would be normally instantiated as the first process. And we are instantiating a browser window with certain preferences. So in this case, we have node integration false. Context isolation false is already the default behavior, so that doesn't affect the overall behavior of the application. And what we're doing here, we're calling a preload script called render.js. Apologize for the confusion of the file name, but that's how this tool works. And the content of render.js is this part. So we're appending a static string to window.abc. And then we are simply prompting that value. So if I run exactly in this way, we expect to see the value of the string. If we now redo by making context isolation true, the preload script, so this object, this window, and the render are in two completely isolated words, so that does not work, and we get an undefined. Let's now talk about security model. You would expect from Electron being based on Chromium to be comparable to a browser, and in regards to security model to also have the same security model. but that's actually not accurate because Electron is important to remember it's not a browser. And even from a design perspective, what Electron is trying to achieve is giving flexibility to software engineers and developers to build something that can use native system notification and native capabilities, which are obviously not possible in a full browser. And so Electron maintainers had to balance, and still have to balance, the usability for developers and the security. And so certain mechanisms that are available on the browser today, by choice or by the current design, they're just not there in Electron. And particularly, let's talk about two orthogonal aspects, one being attack surface. So how do we compare browser to Electron in that matter? So if we think about untrusted content from the web, well, that's why we have browser. Browser gives the ability to browse to random website, which is usually not not possible in an Electron application, unless you're building a browser in Electron, which is highly discouraged. And the Brave browser experiment was an experiment of kind of a failure of not building a browser based on Electron. And in fact, they recently migrated back to a native Chromium-based browser. There is usually very limited interaction. You are allowing people to type input fields, maybe add images, but you never allow a user to go on on random URLs. So in that regards, there is definitely limited interaction on Electron app. It's, for example, discouraged to open a browser window with remote origin. All the guidelines will recommend you to load local resources. On the other side, there are new things that become part of those, a possible attack surface, and this is, for example, local resources. So you can, load resources of any kind from the system, and that would be part of the threat model. So in a streaming application, it is not unlikely for user to download, let's say, subtitles file, maybe download it from torrent or the web within the application. So those are obviously things that should be considered as untrusted input. On the other side, we have isolation. So how isolation differs from browser to Electron? Well, in the browser, especially with recent version of browsers, sandboxing is becoming a very important part. And while there is a Chromium-like sandbox in Electron, because of the flexibility we just talked, it's really difficult to enforce that by default. And if you do need to render content, you may or may not be able to use this property. So generally speaking, in terms of isolation, unless you use the proper settings, the latest version of the framework and all the mitigation that I will be providing at the end of the talk, you should consider that cross-scripting will lead to RCE. And moreover, the exploit reliability is obviously much greater than it would be for a typical memory correction bug, since node integration bypasses, which are the mechanisms to break the isolation, are usually business logic bugs. And if we look at the full chain of an exploit on any Electron app, you can distill this in basically 3 components. So let's start looking at each of them. On the first step, you need somehow to control the DOM. So you need to be able to inject JavaScript. This is typically done through cross-scripting, but there are actually a lot of other ways, including, for example, middle click. And middle click is also a good example of something that is being mitigated by the framework itself in the recent versions. The problem around middle click was that the middle click would generate an event that is not a traditional click event, but rather an aux click event. And so if you would build your application trying to intercept events and blocking the execution, it just wouldn't work because the actual event handler would get a different event. Another good example is drag and drop. Being based on Chromium, you can actually drag and drop URL, and that would force the navigation to that URL. So that's been used for kind of drag and drop privilege escalation, where you drag and drop a content from a render that is not privileged to a privileged render. But this is also fixed by the framework. So since version 3, drag and drop is not enabled by default anymore. So the most common way today is of subverting the flow is through cross-scripting, which is still very relevant, but not very interesting from the pure technical standpoint. I mean, after so many years, I guess we know what is the problem around cross-scripting. Most of the top popular apps are based on React or Angulars. Contextual output encoding is making having cross-scripting more and more difficult. Several apps use CSP as well. So it's becoming more complicated than it seems to actually obtain JavaScript execution. We talked about limited interaction. Also in the context of cross-scripting, if you think about, it's often something that can be triggered by the user itself, which make it not very useful for an exploitation vector. I'm gonna jump for a second step 2 and instead spend a few seconds on step 3, which is basically granted. Like if you are on a render that has, and you have full control of JavaScript, and there is no isolation, or you bypass the isolation, then obtaining a reliable remote code execution is as easy as using Node.js API. And so from the pure technical standpoint, the interesting part, at least in my opinion, is step 2, is how do I go from there is an XSS to bypass the isolation in order to execute commands. And there are a few aspects on why this is interesting. The framework is getting better, at least better than it was 2 years ago when we presented the first research on Electron. There are better default settings, and also people are just learning what are the common mistakes and how to prevent them. So it's less likely if you take a top app that will have the basic mistake of, for example, not enabling node integration. And let's look at node integration as an example. We are tracking vulnerability on Electron since the beginning. There are 12 node integration vulnerability from the inception until February. That's when we made the count. And so the question is, and those are questions obviously we cannot really answer. Are those vulnerabilities sparse or dense? How many more are out there? There are probably more out there. Like, I mean, I do expect to see more node integration bypasses. But if you look, for example, at something that was in 2015 or 2019, you clearly see a difference, which is what is the configuration that was affected by the vulnerability. So in 2015, the one you see on the left, it was basically the default browser window. That's something that every single app has to use. On the other hand, in 2019, which was the most recent node integration vulnerability, it only affected a new feature, which is browser view, with 2 particular attributes, and both the object and the attributes are experimental at this point, right? So it's clearly setting a difference as for the applicability of certain node integration bypass. If you take a random application, you need to really have this specific configuration in order to bypass the integration. How you exploit those, it didn't really change much. It's basically always triggering the opening of another browser window, somehow piggybacking some details. So I mentioned that secure settings are, getting by default. I do remember 2 years ago at Black Hat Vegas mentioning that Electron V2 would be the game changer for security. It didn't happen, but it's now confirmed it will happen in version 5. where browser window will have important security by default. So all what we discussed so far will be there, forced by the framework by default after April release. If you look at Chromium upgrade, so how Electron keeps Chromium updated, it's also getting better, right? They are catching up much faster. There are more resources allocated for the project, more companies that are investing. And so this is all bringing to a kind of a point, which is, security-wise, the framework is getting better. We run our tool, so we have an open source tool that has security checks that can be, can be automated, and we automate it to run on all open source Electron application. And just to give you some number, like what we found, for example, that over 80% were using node integration. So this again brings back the point of people are aware of this problem. Of those, though, only a small percentage, 25%, is using context isolation, and we'll see why that matters. Sandbox, while it's still experimental, there are people out there today trying in production, so that's also good news. And then, yes, a lot of people still don't update Electron to the latest release. So if you would want to kind of summarize what is the state of security for Electron, and I see a lot of discussion on Twitter around that, so that's my personal opinion, which is, it is true that Electron vulnerability have higher impact, and if not properly configured, XSS means RC, but they are more difficult to trigger. It is not just like browsing a page on a browser. And if you look at an important application, the application that we rely on every single day, all applications in this category have isolation in place in some way or another. And from an attacker perspective, what is important is, okay, if I have an application that is using the latest version of the framework and has all the secure settings, what else can I do? And here is, I would like to introduce you this new class of vulnerability called, insecure preload. So insecure preload, in particular preload, is something that I think it's been neglected by a lot of people, and the vulnerability we found on very popular apps, demonstrates that. It is a problem that's been known in the Electron maintainers community. It's somehow being, advertised on the security page, but as a minor issue, and I don't think it received the level of attention that actually it requires. And so there are four main categories or topics around how you can make your application insecure by mistakenly doing something in a preload. And so we'll now cover each of them in greater detail. Let's start with the first one, which is probably the most easy to understand, which is the preload has access to node primitives, and as such, if you mistakenly brings object from the preload back to the render, basically you are defeating the purpose of the isolation and the preload, which is obvious for certain modules, like for example process or file system FS, but is probably not that clear for things like buffer, right? And even the Electron maintainers were exposing by default buffer, and I'm talking about node buffer, to the window object, even when node integration was disabled, and this was used as a node integration bypass. So the first thing that can go wrong on preload is obviously you should not reintroduce Node.js primitive. Again, obvious for certain modules, less obvious for others. So every time you introduce something, it really takes the time to figure out the implication of that. But let's go into the second category, which I think is the most interesting one, and it's about exposing dangerous primitives. And we'll see this example with a very popular app, Wire, which is an end-to-end encryption messaging app. They market themselves as most secure collaboration platform. And the way the desktop app, so we will be talking here obviously about the desktop app, is built is by having a browser window that has not integration false, but allow web view, and then the actual content of where you render the messages, it's inside a web view. So if you are, any XSS on wire, beside of potential XSS in the settings or like very minor windows, will be inside that web view. And they do enforce isolation, but they also load a preload, which is the one you see which you see a part of that. And what this preload is doing is appending a logger, which is used to, as the name suggests, to log information. This is obviously something that it is required in the render, because the overall purpose is to actually log something inside the render, so inside the page that display messages and attachment and such. But unfortunately, if you have JavaScript execution there, then you can repurpose that function. So you see here how this can be abused. We have to jump, for demonstration purposes, we have to jump from the initial browser window to the render. And then inside the render, we can reconfigure the formatter and the transport of the logger to, for example, write to a file instead of to console. And at that point, exploitation is as easy as reinvoking the same function. So let's look at the demo. All right, so this is the app. Will be slowly loading, I guess. Yeah. And here you have the developer console of the primary window. So as I said, we need to switch first of all to the web view. We now have the developer tools of the render that is actually containing the messages. And so what we do here, it's a kind of 3 steps. So the first step, we just change the formatter. The second step, we set the transport. You can see here to, in this case, just to write a file on, just write in bash rc, and I'm not overriding. And then with the simple commands, we can just trigger a logging error. And so at this point, when, for example, I open a new terminal, you will actually get a calculator because we override the file. So this is a first example of a functionality that can be abused, even though it is expected to be used within the render. Let's now talk about a different software, Discord, a very popular messaging app, especially for gamers. The isolation in this case is done directly through a browser window. So the browser window itself doesn't have primitives enabled, but it has a preload. And so let's look at the part of the preload where it's loading native modules. And what this native modules is doing, it can be used to require local modules. And so by reviewing all the modules that were present in the application, we found one that was called XXC8. If you Google for that, it's a better child process, which is always promising when you Google and you get this type of results. So in this case, it's much easier than the wire examples because you barely just need to use the functionality that is kind of exported. So if you think that's too easy, well, let's analyze another example on the same application, just a different version. The same preload script also was importing this module called IPC. What is IPC? It's, if you look at the code, right in the middle, you see IPC render send apply. And then just below, you see IPC render on, it's passing an event. This is basically just a wrapper to the native IPC that Electron has. And it's, it's used internally by Electron itself. So to understand what is the implication of that, let's do a quick recap of how IPC works for Electron. So in Electron, you need to communicate between main and renders, and the way it's done is through synchronous or asynchronous messages. So let's start with the synchronous, the easiest one. On the main, we define a listener. That's the synchronous message, IPC on synchronous message. And on the render, we can just send a synchronous message through a send sync. And the important things here for you to remember is that the only thing that really matters is the channel name, which is the first argument of those functions. In a similar way, asynchronous messages works, but of course it's asynchronous, so you need to have listeners on both render and main. And there is actually no separation of channels, even in the internal Electron code. So the one at the bottom is actually the example of how Electron implemented the alert box. So when you do window alert on a render, what the render does, it sends a message of channel Electron underscore browser view underscore window underscore alert, and that's the code executed on the main. What that means is that we can actually leverage the internal Electron IPC. And so here is an example of how you would basically craft some JavaScript to send IPC messages that would trigger the execution of in this case, of a calculator. We basically use the native Electron functionality. So we do a require by sending a channel, like a message to the channel Electron browser require. And so on, right? So, so far so good. But this obviously, it has one point, which is you need to be able to send IPC messages, which normally it's not available on the render because you don't have access to the first line, so they require Electron IPC render. But back to the Discord bug, if you remember, we actually had an handler of that IPC, despite the fact that we didn't have a way to obtain actually references. And so we've been thinking, okay, how we can abuse that? And then pretty quickly realized that we actually don't need to obtain references. So an exploit for this vulnerability, it actually just involves using, in this case, was asynchronous messages, where we first send a message to the browser require. Child process will be in the stack of the object, and then we just simply try to send another message to call. And obviously, this call will be executed on object that has nothing to do with child process, but we don't care as long as eventually it will actually be invoked on a child process. All right, so let's look at the two demos. Hopefully, so Discord patching and upgrading is pretty aggressive, so hopefully they haven't patched the app that I have locally installed here. So the first one is, the native modules. We're doing nothing else than just native modules, requiring the modules, and this is a module that is bundled with the app. And so, obviously we execute this one and we get a calculator. It is in a different version, so for the other one, I'm going to show you a quick video not to have too many virtual machines. So this is, again, Discord. You can, we can go through the, oops. So this is pretty much the one I was on the slides. We are using the require, and then that object will be allocated and just waiting for us to be executed. And of course, it's all client side and it's all triggered through JavaScript, so it's pretty fast and even too fast in my videos. Another aspect, and so here we go into the third categories of why preload can be bad. It's around sandbox bypasses. So node integration is usually not enough. Like if you have something that comes from untrusted resources, like you load the remote page, you do really need to use Sandbox. And Sandbox makes possible to have a Chromium OS sandbox. It used to be necessary to specify command line argument. It's not true anymore. So with recent version of Electron, you can have app-enabled sandbox, and this will be the same code that Chromium is using for sandboxing, with one caveat, which is there are obviously all the additional IPC messages that Electron uses. So if you have a browser vulnerability and you compromise a render, it is most likely much easier to actually do a sandbox escape as it is on a native Chromium. But nevertheless, this is the best it gets as to getting a render that is equivalent to a browser. However, if you have a preload again that is exposing some of those primitives, we go back to the problematics around introducing objects. So at the bottom, for example, we see cases where if you expose again the app object, or if you expose the IPC render, and it is possible even if you have sandbox, if you explicitly do it in the preload, then we turn back to the ability to send arbitrary IPC, which again, it can be triggered for, can be used to trigger native Electron functions. And finally, let's cover missing context isolation. If there is something you need to bring back home today is if you have an Electron app and you don't have context isolation enabled, it's basically like not having node integration disabled. After some time, I was able to modify the security page of Electron, and it's called native capability and your responsibility, to actually explicitly mention that you need to enable context isolation. So to recap, if you don't have context isolation, it's like you have a permanent node integration bypass. And this is by itself, I would say, a completely new class of vulnerabilities. Masato is, all credits goes to him. And thanks to his work, Electron introduced this new setting. For the context of preload, this is also very interesting. And so that's what we'll be covering today. It's how can you use the missing context isolation in the context of preload? And so the idea is that if you don't have context isolation, render and preload share the same context. So changes in the render affects the code that it's been defined in preloads. What that means is that we cannot guarantee the integrity of that code. And again, I will show you with like a real life app that has been redacted, a trading app, where it would have a single browser window with both node integration disabled and sandbox, which again, you would expect to be the best security configuration out there. And it was using the most recent Electron framework at that time. And if you look at the preload, we had a code similar to this one. It was a bit, it was a little bit refactored with changing a variable name and such, but this was basically the same code that was there. And this is actually trying to prevent the common channels, right? This is exactly trying to prevent the vulnerability that we found on Discord, where you are evaluating what is the channel that the render is sending messages to. And it looks good, unless you realize that you don't have context isolation. So if you don't have context isolation, you can use prototype pollution to override, in this case, the include function. So if you look back, you see here that there is an if statement where we are checking if the specific channel is part of the IPC whitelist, and it's done with the native includes, array includes function. But this can be bypassed by simply doing array prototype includes. They always return true, and after that, just invoke your code, and in this case is, again, leveraging the same technique and basically the same code that we prepared for the other IPC abuse. Just as a matter of reference, you also need to know that prototype pollution and the problem around context isolation affects things outside of preload as well. So Masato has done an amazing research. You have the slides here. The bottom line is that you can override the call function, and basically one of those arguments of the call function at some point of the application execution is actually a process object, and so you can leverage the process object to get back access to node. As an example of an application that is vulnerable to that, and again, this is applied to basically all applications that don't use context isolation, with some caveats, but most of them, is Mattermost, which is a Slack clone type of application, uses a web view inside a browser window. And so I will be showing here briefly the demo. So here we have Mattermost. This bug is not patched yet. They are aware of the issue. Enabling context isolation is not trivial. So what we're doing here, we are doing a prototype call where we are overriding basically we're piggybacking on the arguments, and at some point the execution will actually bring as the argument a process, and once we have a process we can use main module require to get access to other modules. And so the first part is actually giving access to is basically overriding, doing prototype pollution, and then the last part is triggering an event, in this case the reload, which trigger the execution of a call with one of the arguments being a process. So what are the solutions around context isolation? Or rather, if you enable context isolation, as I demonstrated at the very, very beginning, you can't export things to the window. So how do you do? Well, for the preload problem specifically, you can use VM context, which basically you can programmatically create a new context. This will solve the problem of preload. It will not solve the problem around context isolation affecting the Electron code, but it's better than nothing, and it's easy to implement because it's just about adding code to the preload. The real solution to this problem is having context isolation on and using post messages instead of just appending object to the window object. If you have very complex messages that you need to pass around or very complex objects, there is Electron valence, which is a module that allows you to serialize and deserialize objects. So to go through the conclusion, it is possible to build Electron applications that are secure. You really need to know the framework. It's evolving very fast, so you do need to spend time figuring out how things are changing and what are the new settings that may be relevant for security, for example, like context isolation. The first best advice I can give you is do not load remote content. The entry point is always navigating to some attacker provided a page in order to execute JavaScript. So XSS and all, the old school vulnerabilities still apply. So use a modern JS framework that already protect against that. And then on top of that, you need to have secure configuration. But after this presentation, you hopefully understand that you also need to pay attention to what you are exposing in Preload, particularly around dangerous primitives and IPC. We released the tool. We just released a new version that has a bit more checks on our GitHub page. So you can use this tool to scan for basically those common vulnerabilities. And with that, it's just 45 minutes. We have 5 more minutes, so I can take more questions if there is. No questions? Let's see if we can get at least one question.
Did you say the Mattermost vulnerability, there's a patch for that? Or?
No, it's not there is no solution, meaning it's the latest version is still vulnerable. The reason it's in my presentation, it's a public bug, so I didn't see the need of obfuscating something. It's on the internet already. But the problematics around context isolation is that people have been traditionally appending stuff to the window object. And so migrating from this type of designing application, it's not a one-line code change. So it does require some time, and Mattermost approach is because it does rely on having an XSS or having a way to redirect the user execution to an arbitrary JavaScript. It is not an exploitable vulnerability by itself. There will be, my understanding is that they will be fixing this bug. Again, there's an open ticket, and I see some traction. I think it just it does involve redesigning a bit of the preload. Not really. No, it's any workaround would rely on modifying the application. So if you enable context isolation, the app will break. So it's not even possible to say, okay, I want to just lose some features. That's just not possible. Thanks for asking at least a question. Well, thanks a lot for listening.